For more than 100 years, Schneider Electric has been an industry pioneer of market-leading solutions. As the engineering landscape rapidly changes, no one feels the impacts of the mounting challenges like consulting engineers. We understand these challenges. We face and solve them with you every day. Projects are becoming more complex, faster moving, and the connected world demands immediate answers while margins grow tighter. As an expert in your own right, we're set on making sure that you're equally matched in the manufacturing company you turn to, which is why we're launching PROficient for Consulting Engineers, a suite of services and tools that gives you unparalleled control from design to implementation, solidifying a real connection between highly qualified professionals. PROficient is built on a foundation of E2E, or expert to expert. Through innovative technology, responsiveness, and industry-leading BIM advancements, PROficient is tailored for you. All backed by market-proven Square D and Schneider Electric products with matchless service and support, we're delivering expertise that enables you to excel. You spoke, we listened. PROficient for Consulting Engineers. Expert to expert.
Good day to all. Welcome to PROficient for Consulting Engineers and our Expert to Expert webinar series. Today's topic is gas-insulated switchgear, sponsored by Square D by Schneider Electric. I'm your moderator, Wendell Leisinger, the Segment Manager for Consulting Engineers. I would like to go through a little bit of information in advance. Please join our Consulting Engineer portal. Through this portal, be able to get the continuing education modules and ability to manage your courses and education credit certificates. Also, you get direct access to some of our tools, models, design apps, calculators, and others, and updates in the latest in products and solutions to give your designs the needed edge. Additionally, your desktop and the various icons on the bottom of it, the yellow box controls your slides. That slide area can be enlarged, such that it is better or easier to view. Also, there is a green resource folder. That folder gives you access to our PROficient for Consulting Engineers website, today's presentation, and also a link where you can create your PDH certificate for attending this event. Please ask questions throughout the webinar by clicking on the question and answer icon. I'll be reviewing these questions as they come in and giving them to the presenter as appropriate. Please note it's very important also on the far right, or the last one, the survey icon, to give us your feedback. Feedback's always warranted to make certain that we are meeting your needs and continue to do things with these expert to expert webinar series that makes it very useful and informative. So please take the survey anytime that you have an opportunity. And also we have social media links to our presenter in LinkedIn and Facebook. Before we get started, I'd like to ask a couple of quick polling questions. So now there's a polling question. How would you characterize your knowledge of gas-insulated switchgear? Please take a moment and respond. Let's take a look. Most of you are most of you, or half of you, know about GIS. Others, this may be a new concept for you. Excellent. We would like to share our background on GIS. One more question. What is your current perception of gas-insulated switchgear? And you can check all that apply. I know nothing about it. It's ultra compact. It's unreliable. Now let's take a look at your responses. Obviously, for those that had not heard of GIS before, you know nothing about it. Okay, great. It's ultra compact. Our learning objectives today is to make you informed of what is considered gas-insulated switchgear, GIS. Also, how GIS addresses the needs for the U.S. market and what are the benefits. Also, our presenter will get into optimizing a single line diagram considering GIS and learning the operating and maintenance differences between metal clad and GIS for your clients. One more polling question. Do you currently specify equipment that has SF6? For example, SF6 circuit breakers or SF6 switches? We'll move quickly through this. Indeed. I would like to introduce our presenter today, Philip Reamer, Medium Voltage Product Manager. Phil has extensive experience in square D metal clad and metal enclosed switchgear as well as arc flash mitigation techniques. With that, I'll turn it over to Phil.
Thanks, Wendell. I really appreciate the introduction. And thanks, everybody on the line for joining today. Hopefully this presentation is going to be enlightening and interesting for everyone online. So without any further ado, I'll turn it over to the first slide here. To make sure everyone here is kind of on the same base here, I want to show this slide about different areas where we use SF6 in electrical transmission and distribution. So for starters, you have some high voltage switchgear on this. You have station breaker, pad mounted switchgear, recloser, and in the middle we also have Square D's HVLCC metal enclosed switch. So the main objective of this slide that I want to propose is that we use it in a lot of different areas, but not all of these items are considered gas-insulated switchgear. In fact, only one of these is not gas-insulated switchgear, and that's the HVLCC. I'll get into a little more detail about why HVLCC is not GIS and what makes these other products gas-insulated gear. We'll get into that in a couple more slides, so we'll move on. So why GIS, and why have we evolved in this direction over time with switchgear design? This all started way back in the advent of AC circuit breaker switchgear, medium voltage switchgear. In the 30s and 40s, we had open air switchgear. And over time, we've evolved towards now air-insulated metal enclosed switchgear, air-insulated metal clad switchgear. The objective here is to optimize the design for safe and easy troubleshooting and maintenance of switchgear. Now, however, from the 80s and beyond to today, gas-insulated switchgear has been designed with a different thought in mind. This is in order to prevent faults. So what this means is that we are eliminating a lot of the common causes of problems or faults in switchgear, and also addressing a lot of key issues with switchgear application in buildings. So that's when we get into compactness as well as cost. So like I said 2 slides ago, what exactly is GIS and why are some products not considered GIS even though they have SF6 inside? I've boiled it down to 3 main points here. So number one, Gas-insulated switchgear is switchgear that, of course, incorporates gas. Typically, that's sulfur hexafluoride or SF6, but sometimes it's other gases at higher than ambient pressure, and it's used as an insulating medium. Another point is that, now this is kind of a general point, is that the contents of the switchgear include, circuit breakers, switches, bushings, buses, pretty much everything that you might include in a standard switchgear section. And the last thing is the real kicker here, and it's that in a vertical section of switchgear, some or all of the medium voltage compartment is comprised of that gas pressure system as the primary insulating medium. Now, the reason why there's some or all rather than all compartments is because of what I'm going to talk about in the next slide. So this slide is talking a little bit about the evolution of GIS. Originally, the early designs of gas-insulated switchgear were very large pressure vessels. The original designs were in the high voltage arena. And so in there, you have to have a pressurized tank for each phase. And all the bus, all the breaker, every component is insulated in gas. Well, now in modern day, and what designs, particularly in medium voltage, have evolved to is a combination of not only SF6 insulation. You still see bus bar insulated in gas, and your medium voltage circuit breaker or switch insulated in gas. But now we're seeing a combination of gas insulation as well as solid insulation. So a silicone-based shielded insulation on bus bars and, of course, cable connections, which reduce the amount of gas needed in each section. So I really want to emphasize on the slide that we're kind of evolving from this older design concept into a more modern design that incorporates different technologies and also reduces the amount of gas compartments and a volume of gas needed on site. Now to make sure that we're all kind of pretty familiar or more familiar with the gas that we typically use as an insulator, that's SF6. So SF6 stands for sulfur hexafluoride. It's a harmless gas in its natural form. It's actually an inert gas similar to helium, except rather than being a light gas or very not very dense gas, it's actually a very dense gas. It's 5 times heavier than air, and we use it because of its high dielectric strength, its great ability to extinguish arcs, and also because it is a self-healing gas and it is very resistant to the effects of pollution and temperature change. It's not only used in electrical transmission and distribution. It's used in a lot of different areas. It's in ultrasounds, tennis balls. Also, it was used in the Nike Air bubbles as well for quite some time. Now, a key point with SF6, and probably what most of you on the phone are familiar with, is that it is a greenhouse gas. It has a much higher global warming potential than carbon dioxide. And so that's why there are some careful steps being taken to ensure that we limit the amount of leakage and reduce the total amount of gas needed in medium voltage switchgear. There have been studies, however, like this one cited on this slide, which show that over the total life cycle, considering particularly hermetically sealed, but not only hermetically sealed gas-insulated switchgear, that over time, gas-insulated switchgear actually contributes less to several different factors, including global warming potential, acidification potential, and the nitrification potential, than some open-air switchgear. So although we utilize SF6, which is a greenhouse gas, it also helps reduce the effect of the switchgear on the environment as well. So That's why we one of the other reasons why we still use it in the industry.
Phil, we do have a couple questions in regards to the gas.
Sure, yeah.
One question, it's a two-part question. One question, why must gas be under higher than ambient pressure?
It actually doesn't necessarily have to be, but it commonly is because as you pressurize the gas, that means you have a better insulated. It insulates better than non-pressurized gas inside the tank, and so that allows us to get things even more compact. In other cases, people will pressurize gas to increase BIL rating or some other electrical ratings in the switchgear.
Great, thank you. Second part, I thought gas was only required where contact make break under load.
No, so that mostly pertains to some specific circuit breakers or old switches where the interruption was being done in SF6, and there still are SF6 circuit breakers out there on the market. In fact, one of our own gas-insulated switchgear products uses it's a SF6 circuit breaker inside a gas-insulated tank. So it doesn't have to be used in a make-break area. It's actually more commonly used now in medium voltage just as an insulator because we use vacuum interrupters as the making and breaking component.
Great. Thank you, Phil.
You're welcome. So moving forward, I have some general slides just to talk about why we use GIS. We've already talked about one of them. Looks like I got to work on some of these animations here. So three main things that I want to focus on for GIS. One is we want to ensure people's safety. So with GIS, you get arc resistance. Most products on the market are arc resistant either to the IEEE standard or to the IEC standard for arc resistance. And also, because we use it's a sealed pressure system, that means that there's no maintenance inside the medium voltage compartment. And because there's no maintenance there, that means workers are no longer exposed to the risks of working on medium and high voltage components. Next point is continuity of service. So again, GIS is designed to avoid failure. So because your medium voltage circuit is insulated in gas, that means you're not exposed to dust, you're not exposed to humidity, you're not exposed to a lot of the external influences on the circuit which make you have to do maintenance and also cause problems down the line with switchgear. And then finally, lowering the cost. So in the poll, initially, not everybody, but the majority of the perception is that gas-insulated switchgear is compact, and that's true. That means that you can, if you're designing an electrical building or an e-house, you can drastically reduce the amount of space that your medium voltage gear takes up, and you can shrink down the house, shrink down your HVAC system, which can drastically reduce the total cost or capital expenditure of your switchgear. In addition, and we'll talk about this later, is you also reduce your operating expenditures because you reduce maintenance. So this slide is a really good slide. I really want to share it with everybody and focus on this one for a minute. So this is talking about a study from the IEEE Gold Book, and it showed the share of air-insulated switchgear failures and the main causes of that. So this went through everything from abnormal operating conditions to mechanical damage from a foreign source, that being either someone doing maintenance or from some other cause of mechanical damage, all the way down. And with gas-insulated switchgear, we can say that over 50% of the failures of these common failures in air-insulated switchgear are not relevant to GIS. So going through a couple points here, exposure to moisture. Because your switchgear or your medium voltage circuit, your live parts are sealed in that gas-insulated tank, you have no exposure to humidity or salty or caustic, polluted environments. So you reduce that effect on your switchgear. Critters, animals, just getting inside the switchgear and causing an arc. That has happened. I'm sure everybody has heard of horror stories like this. And because it's a sealed for life tank, again, or a sealed tank, you eliminate the ability for animals to get in there and cause problems. So just from this slide alone, you can see the great value of GIS. On top of that, we get into compactness. So if you compare just the real estate that GIS section takes up compared to an air-insulated metal-clad piece of switchgear. Now here we're focusing at 38 kV. You can just see that it's vastly, vastly more compact. In addition, most GIS manufacturers do not require rear access. So also when you're trying to shrink down an e-house or really optimize your layout in a building, you don't need rear access. Cables or terminations are typically accessible from the front or from the bottom through a gallery. That means you can again save on space and save on money there. And the final thing here is reducing costs. So we've already talked about two of these. The combination of reducing maintenance, because you do not need to maintain anything inside that gas compartment. And because your switchgear is much more compact, you can minimize the total cost of ownership for yourself or for the customers, the end users, which everyone appreciates and can't really ignore. So with that being said, how do we really compare to air-insulated switchgear? This is kind of the big talking point, mostly in the U.S. where gas-insulated switchgear is kind of in its infancy. So the main points I want to address with the next couple slides here is the design objectives of the two types of switchgear. So first, with air-insulated switchgear, I talked about this at the beginning, and I'll talk about it again, is the objective is to make it easier to maintain the switchgear and make it as safe as possible to maintain or troubleshoot the switchgear. So the assumption is that you're going to have many failure possibilities in the bus bar compartment or with the circuit breaker. So the idea is to make it as easy and safe as possible to replace that failed component. So this doesn't necessarily address the causes of a lot of these failures. So moving on to the next slide, the design objective here is eliminating faults. So this is because you, again, eliminate maintenance needs, and you eliminate the need for access in certain compartments where you might see a common problem. So here that kind of summarized the two different concepts that we're looking at. Air-insulated switchgear designed to maintain and repair and minimize shutdown time in that area. So the main deciding factor for air-insulated switchgear, in the cost analysis at least, is it's based on CapEx. If you're not looking at operating expenditures, then CapEx is going to be the deciding factor for air-insulated gear. On GIS, it's designed not to fail and not to maintain. So your cost analysis then becomes twofold, where you base it off of CapEx, how big your e-house has to be, or how big your building has to be, and also how expensive your switchgear is. And as well, analyzing the operating expenditure, so how you can reduce the cost of having to maintain switchgear, and also over time looking at the probability of faults. If you can reduce the probability of faults, you can drastically save on possible future downtime as well.
So Philip, before you jump into substation design, there's a couple more questions.
Sure.
One question, what does it mean, no maintenance? I've never heard of no maintenance switchgear.
Right. When we talk about no maintenance, we're focusing specifically on maintenance of the medium voltage circuit. So that means your vacuum interrupters, for this you have a three-position, typically you have a three-position isolation switch so you can isolate and ground the circuit breaker and cables. Anything that's inside that gas compartment, which is a medium voltage part, does not require any maintenance or inspection. Now, typically you do need to inspect the operating mechanism or inspect just the panel in the front, maybe at every 3, 4, 5, or even longer years. But the point here is that it's not, there's no breaker to rack out. It's fixed mounted circuit breakers. And there's no inspection of anything inside that gas compartment, which that's the real time-consuming part in switchgear. Looking at some of our Schneider products, I know typically the routine maintenance is a visual inspection of the switchgear and an inspection of the mechanism of the circuit breaker outside the gas tank. So you're never exposed to medium voltage. You maintain arc resistance during the maintenance cycle, and this is something that can be done in a matter of minutes rather than a matter of hours. That's what we mean when we say no maintenance. It's no maintenance of the medium voltage circuit.
Great. Another question, how about 12 kV, 15 kV, or 5 kV switchgear?
Right. So now we'll just call this the 15 kV class of switchgear. The main difference that you're looking at between air-insulated and gas is that air-insulated switchgear, we'll focus on metal-clad for simplicity. Metal-clad, you can typically have a too-high construction. So when you compare too-high construction versus GIS, which is single-high construction, so when I say single-high and too-high, single-high, 1 breaker per section, too-high is 2 breakers per section. There is an analysis that has to be done to compare, number of breakers for the whole footprint of the lineup. So I'll never say with 100% assurity that a GIS lineup at 15 kV is going to be more compact than metal clad at 15 kV because there's sort of a break-even point. But in a lot of cases, if it's a simple lineup and you take into account the reduced risk of fault, arc resistance, that can move you to choose GIS over AIS. There are also some extra compact products that aren't gas-insulated switchgear but use gas components. Like there's a new Schneider product out there called HVLC-B, which uses a single-high fixed circuit breaker with our HVLC-C 3-position switch. So it's more compact than masterclad or metal-clad switchgear, but still maintains a lot of the benefits or similar concepts to gas-insulated switchgear without the gas insulation, of course. That adequately answer the question, Wendell?
Very nice. Yes, one last question regarding maintenance. Is there a need of exercising and or testing the operation of the switch?
So yes, typically there may be an exercising of the circuit breaker mechanism, but that's it's not completely necessary. It just depends on the typical maintenance practices. But yes, typically there's a cycling of mechanisms just to make sure it's operating correctly.
Thank you, Phil.
You're welcome. All right, so with that, we'll move on. We're going to talk in the next group of slides about substation design, installation, commissioning, operation, and maintenance. So first one, substation design here. I just want to talk a little bit about how you can optimize a single line, taking into account the design characteristics of GIS, because it isn't the same as metal-clad or air-insulated switchgear. So there are some different approaches to different types of protection. I'm going to focus on these 6 concepts. We're going to go all the way from a standard single bus arrangement, so that when I say single bus, this is everything from just a main with feeders to main time main with feeders or the like, all the way down to ring bus configurations. On the left, skip through a slide real quick. Sorry, everybody. So on the left here, single bus, the air insulated point of view, we're going through maintenance and then faults. So maintenance, probability that you're going to have maintenance on air insulated switchgear, it's mandatory. We know there is routine maintenance on medium voltage switchgear and metal clad. Typically when you have maintenance of either the bus bar or of the circuit breaker, you're either having a total shutdown of your lineup, or you're having a shutdown of a specific circuit, depending on if it's a circuit breaker that you're doing maintenance on or if it's the bus that you're inspecting and maintaining. In addition, faults here, it depends on the switchgear reliability, so manufacturer to manufacturer it's different. But the consequence of a fault in the bus bar, of course, is a total shutdown, and the consequence of a fault in a circuit breaker or circuit breaker compartment is a shutdown in specific circuit. So with air insulated switchgear, and the reason why you have routine maintenance, preventative maintenance, and a lot of these new preventative maintenance practices, is that it's assumed that this is a lower reliability type of design. However, the cost of this is pretty low. When you go over to gas insulated switchgear, the point of view there is that maintenance, of course, is not needed in the bus bar compartment or the circuit breaker. However, if there is a fault, either of the circuit breaker or the of the bus, you might have a total shutdown or a shutdown of a specific circuit. So the consequence is the same, but your probability that you will have a fault or a problem in one of these compartments is very low, and that's because of a lot of the reasons that we've already discussed early in this webinar. So the conclusion here is that for a single bus arrangement, you get much higher reliability at a still low cost because it's a simple design here. So the next one is a main or transfer bus. So typically transfer bus, you have it to have some auxiliary power, or you still have power during a maintenance cycle. So from an air insulated point of view, you increase your reliability here. You still have maintenance of your circuit breaker and bus. But with this, you have an increase in cost as well. Now from the GIS point of view, typically transfer bus is not needed. So typically as an alternate to transfer bus, we would propose a more simple and cost-effective just a single bus arrangement. This is because you don't need to have that routine maintenance on the circuit breaker, and you don't need to have that routine maintenance or inspection of the bus bar. So you get, again, the higher reliability of the GIS, and you keep your costs much lower because it's a lower complexity of design. Now again, a double bus with a double breaker. This is a similar kind of design concept to transfer bus, but in this case, you have redundancy of your circuit breaker. So you have potentially you have protection of your alternate bus here. So you have an even higher reliability of your air insulated switchgear, but the cost is extremely high for this because you have completely redundant bus and completely redundant circuit breakers. So you can double, or if not more, increase the cost of the switchgear lineup. And I'll go back to again to that same logic here, is that because we're not having to do maintenance on the switchgear routinely, because there's such a low probability of faults in gas insulated switchgear, we can propose a single bus as an alternate to this, just because you don't need the duplicated high reliability of switchgear. So if you do choose to do a double bus, double breaker arrangement with gas insulated switchgear, it can be done in many cases, and the cost is also very high. Second to last one here, double bus and a single breaker. So this is a a selective bus bar arrangement where a single circuit breaker can select from an A or B bus bar source. From an air-insulated switchgear point of view, you get high reliability here. The cost here is lower than that double bus, double breaker arrangement. So this is where one of those cost analysis really has to be done as far as reliability and cost. Because the cost here is lower than your double bus, double breaker, but it's still quite high. And then on the GIS side, you get extremely high reliability with this type of arrangement because you have a secondary bus, another bus that you can pull from that. In the unlikely event that you did have an issue and you did have to shut down one bus, you still have another source and you can maintain your uptime at your facility. So this has an extremely high reliability, but the cost of this configuration is also quite high. Now the last one is a breaker and a half or ring bus configuration. So the main point of this slide is when we're in the medium voltage arena, typically it's not very economical to have a GIS lineup in a ring bus configuration or breaker and a half configuration, just because of the complexity of the bus bar configuration, the complexity of the protection that's required for this. Typically a ring bus and a breaker and a half scheme is something that would be more cost effective and at least of more use in the high voltage arena, so at a high voltage substation, a high voltage gas insulated switchgear configuration. So you can do it in an air insulated point of view, and because the switchgear is very flexible in that sense, where you can do a variety of bus bar configurations or a fully customizable bus bar arrangement. It is possible. However, with GIS, it's just typically it's not achievable from a cost perspective to the customer. So after going through all these, I think you all get the main message is that with GIS, because of its extra reliability and because of its safety and reduced need for maintenance, we can simplify a lot of the complex configurations out there and therefore reduce the cost of a lot of medium voltage substations just by changing the single line to a much more simpler design. Now protection is another area where you can focus on for cost reduction by utilizing gas insulated switchgear. So traditionally in the U.S., we see that we have a lot of bus bar differential protection, a lot of circuit differential, so isolation of the circuit breaker is a failure point. The proposal with GIS is that there's no need for or no use of bus bar differential, and there's no need for overlapping protection of the circuit breaker, simply because those are not common failure sources. So you can simplify your protection and therefore simplify or lower the cost just by eliminating those extra relays and extra instruments. So here, bus bar differential, of course, and then eliminating that overlapping protection of the circuit breaker, because the circuit breaker, the only failure point in there is a vacuum interrupter, which is a highly reliable component in GIS. So Wendell, before we get moving in the last bit, do we have any questions? Or
you have a lot of questions. We probably won't have time to address them all today on this webinar. However, we will answer all questions through our systems. Here's a question. Is this gear close coupled available?
So typically gas insulated gear is not close coupled like with a transformer or a motor control center. Reason being is that it uses most GIS switchgear uses a very special bus bar configuration, whether it's all sealed in gas or even if it has a solid insulated and shielded insulation. It's a very unique bus bar configuration. So typically what we'll do is we'll cable down the bottom. Most if not all GIS switchgears are bottom entry. You can cable down and then into an adjacent transformer or a motor control center or something like that. At 38 kV, typically there is the size change between GIS and then air insulated switchgear, or between a large transformer, is very different. So close coupling it can be done just with an adjoining piece of sheet metal, but there's not a direct bus bar connection typically with GIS to other switchgear or transformer.
Great answer, thanks. Here's one more question. In the years past, SF6 capsule would lose pressure over time. What has been done to alleviate this?
So yes, in the past, that's been one of the main causes for some of the negative perception around GIS, is that it's leaky, and you have to constantly recharge it. So now, modern GIS, so we're talking about the more recent stuff, not the old piping type of design, is typically it's tested to be sealed for life. So with our Schneider products, they are all, it's kind of our own coin term. They're hermetic. They're sealed for life, and as they're discussed in standards, they're hermetically sealed. So we fill the tank in our factory, and we test it to ensure a leakage rate of less than 0.1% per year. So that's very, very low, and this means that there's no need to refill the tank on site. There's no gas handling on site because all the interconnection that's done in this type of switchgear is done with solid insulated connection. So there's no need for gas handling on site, no critical seals are done on site, and so that eliminates those main causes for leaks or long-term issues. So yes, I do agree. In the past, that was one of the common problems, but now with the modern design of switchgear, it's eliminated the need for any of that recharging over time.
Great. Good to know. Thank you, Phil.
You're welcome. So with that, I think I'll keep moving for the essence of time. So we'll go through the last couple of things. We've already talked about this quite a few times, so I'll keep kind of harping on this more. As we all know, it's with GIS, you have a drastically more compact switchgear. Even at 5 and 15 kV, the footprint is much lower, but at that point you have to then think about two high versus single high construction. Another consideration with GIS is installation and commissioning. So GIS is typically lower in weight, it's smaller, so you need less of it doesn't require any special supporting from a weight perspective, especially in a E-house or prefabricated building. With GIS, you do need to ensure that the switchgear is very level, because the connection, the bus bar connection, and for the old style of switchgear, which requires sealing, it requires a very tight tolerance of elevation change from section to section. So with a lot of gas-insulated switchgear, on this slide it's showing CBGS0, one of our Schneider GIS products. It has integrated leveling screws, so inside the frame you can adjust these leveling screws before you anchor the switchgear down, ensuring that you have the gear level across the whole lineup. Operation of GIS is very straightforward. Typically there's an active mimic bus on the front of the switchgear, so this picture here shows our GHA, gas insulated switchgear, for 38 kV. So you have a single line diagram showing your circuit breaker open and close indication, and also your isolation and grounding switch. You have an integrated grounding switch in each section of GIS. The active mimic bus indicates the open or close, but also gas-insulated switchgear typically has a visible break. So as an IEEE requirement, you either have a window or a camera. So on Schneider products in particular, they typically have a camera that's viewable, either plug in via USB through the front to a laptop, or viewable through an HMI on the front of the switchgear. That's the most common option, but there's also windows on some other products to show the visible break. All the operation is done from the front of the switchgear. Grounding is done from the front of the switchgear, and there's integrated interlocks preventing any improper operation of the switchgear or operation of the ground switch. So maintenance of the switchgear. I'll go through these pretty quickly because there's a lot of detail on these slides. You can refer to it later. But the main thing, comparing maintenance procedures, GIS versus metal-clad, you've got essentially no maintenance on the bus bar, no maintenance on the main circuit. Medium voltage parts aren't accessible, whereas on metal-clad, you typically have to inspect the circuit breaker, withdraw it, test BIL. You have to lubricate the mechanism every year. GIS, typically the maintenance cycle is not every year. It's not even every 3 years sometimes. It can be 4, 10, even 20 years, depending on the product. Again, talking about maintenance, looking at inspection points, the number of inspection points on GIS is much lower. So again, that's talking about fewer operations required, fewer points that need to be looked at, which makes it easier for the operations personnel to go through and eliminate any type of extra work. The last part is talking about grounding, because in a metal clad, typically you have to use either you're using a hook stick and some grounding leads, which is kind of the old way of grounding, or you use a rackable ground and test unit, which requires that you remove the circuit breaker and rack in a ground and test device, which may have some very special interlocking on it. With GIS, all of that is integrated into the switchgear, so there's no external devices needed to ground the bus bar or the circuit breaker. All of this is also interlocked so that there's no way of improperly grounding potentially live bus bars or potentially grounding a feeder section or feeder breaker when there is voltage present. So this is just going through those operating procedures, the steps. I won't go through these in too much detail, but all of this is all accessible from the front and can be performed without eliminating your arc flash rating, because it's all outside from the front. No panels need to be open, so the gear is still arc resistant. You're still in an arc resistant scenario. Of course, with metal clad, if you're racking in a grounding device, you have a door open. Even with arc-resistant metal clad, you still have to open a door in order to rack in a grounding device. So you're still exposed potentially to some live parts. So from a safety perspective and also a simplicity perspective, you can see the advantage of having an integrated grounding switch in GIS versus a rackable grounding device in air-insulated switchgear. So for today, that just about covers everything I have. You can see that GIS gear has some added value. The design and philosophy is different. It can be more simple, and it also can save not only on the capital expenditure but operating expenditure of a new installation or existing installation. So the single line operations maintenance are all different, but it can be beneficial. So I recommend that everybody at least give it a try. And if you have any more questions, of course, contact all your people at your contacts at Schneider Electric. With that, I'll give it over to Wendell.
Great, Philip. There's a number of questions if you have a couple minutes.
Sure, yeah.
Here's one that may be right down your alley, and that is, how about seismic anchoring since you require leveling? You will normally need to be seismically restrained.
So no, there doesn't need to be a special seismic restraint. It depends on the manufacturer what they've seismically tested their gear towards. But I can speak towards our Schneider products where they all have been tested and are available with the IBC seismic codes without any special anchoring procedures. So depending on the region, we certify on a case-by-case basis, of course. But yes, they are seismically certified, and of course I always suggest consulting the structural engineer on site in case they do choose to reinforce everything or anything. But we do not require that as part of our standard anchoring procedure.
Great, thank you. Here's another question. How about special cable terminations? Are they required?
So again, it depends on the manufacturer. So I'll speak mostly towards the Schneider offers, but there's essentially two different types of cable terminations in gas insulated gear. One is, I guess the trade term for it is an intercone connection. It's a connection from Pfister. It comes from the high voltage arena. It's typically at 100 kV and above, but they also make it all the way down to 38 kV range. This is a very expensive termination. You have to be specially qualified to not only make the termination on the cable, but install it typically in that switchgear. So installation and just cost of the termination is very high. Schneider, we use a standard dead break elbow connection like you'd see on a pad mount transformer or a pad mount piece of switchgear. So it's much more easier to do. It's also accessible from the front. So a lot of the intercone connection can only be terminated from the bottom of the switchgear, which requires that you have a working gallery beneath the switchgear. With the dead break elbows, it's all accessible from the front, so it eliminates the need for any extra working gallery beneath the gear. Also, that's a more common connection. Most electrical contractors are familiar with that connection. There's a lot of suppliers of those elbows everywhere, so that's why we typically use the elbow connection for our cable connections.
Great, thank you. How about another question? How common is double bus GIS? Where is it usually used? Utility systems?
Yes, it's typically a utility system. I've seen it maybe only on one or two occasions for very, very large oil and gas projects. Typically, though, like I was talking about during the single line slides, is that the increase in cost of doing that double bus arrangement often is not justified. And so even if it's early in the stage of design and they're considering double bus arrangement, once budget numbers come in, it's simplified to a single bus arrangement for GIS. Utilities use it more often just because of the extremely high reliability requirements for utilities. So it's most common in that segment, but I have seen it, once or twice in some very large oil and gas projects, which, of course, are also require a high degree of reliability.
Good to know. Phil, here's another question. What are the typical BIL ratings?
So typical BIL ratings are 150 kV BIL, 170 kV BIL, and you do see it up to 200 kV BIL. So a little bit of detail about this. There currently is not an IEEE standard for GIS. It's in draft form. It probably should be released in the next year or two. In fact, one of our Schneider engineers is chairing the committee, and we've all been very deeply involved on that standard. So most GIS manufacturers, when they either UL list or ANSI test their switchgear, they do it to a combination of the gas insulated standards per the IEC and to the electrical standards for the ANSI IEEE markets. So you typically see a metal enclosed certification, so that's 150 kV BIL there, or the optional rating of 170 kV BIL. And then for some that are converting an outdoor station breaker type configuration to an indoor GIS configuration, sometimes you'll see 200 kV BIL as a rating there, but typically that's not a requirement because GIS is indoor switchgear, whereas that 200 kV BIL rating is coming from the outdoor like station class, station circuit breaker type arena. So mostly where I've seen 200 kV BIL is typically when it's just been kind of a specification that's been just copied over from a different design. Most common is going to be 150 to 170 kV BIL.
Interesting. Another question, does it require air conditioning for the electrical room?
No, not necessarily. Of course, it depends on the location. If you're up in the northern region of Canada, you probably would like to have some form of heating in the electrical room, but you don't need to have air conditioning in there. Yeah. So I'll say it depends, but in most cases you don't necessarily need it.
Here's one question around the circuit breaker interruption. Are the arcs broken into vacuum bottles filled with SF6, or are they true vacuum bottles?
They are true vacuum bottles. So yes, it's a vacuum bottle with nothing inside, and so that's we only use the SF6 as an insulating medium. Even with our Schneider product CBGS0, which uses an SF6 bottle, so that uses an SF6 bottle for the circuit breaker, and then on the outside, so in the sealed for life tank, there's a low pressure SF6 insulation. You typically in medium voltage you do not open and close the breaker inside the insulating medium. That's something that more happens in high voltage switchgear, where we really where vacuum bottles really aren't as available or common. But in medium voltage, yes, we've eliminated breaking the circuit or open and closing the circuit breaker in SF6. It's all in a standard vacuum bottle, something that we also use on a metal-clad draw breaker.
Excellent, great, Phil. This has been very informative. Thank you very much for presenting to us today. I see that we're out of time. I want to let everybody know that any of the questions that we did not get to today, we will answer, and we'll email directly back to you, and then we'll also be sharing the questions with the entire audience so that you could see some of the things that people are asking about and the answers. Also, it's a reminder to please join our Consulting Engineer portal. This is where the continuing education modules are, and be able to get your education credit certificates. There are a number of questions that came in around how do I get my PDH certificate? Where is that? Please bear with us. I have a short video that we'd like to share with you in the next moment or two about our portal, our CE portal, and the power of the Consulting Engineer portal for your uses. After that, we have directions, and we will repost the directions on how to get your PDF certificate or a certificate of attendance. With that, this ends the PROficient for Consulting Engineers and our Expert to Expert webinar series on gas insulated switchgear. Have a great day. Oh, and please take the survey, give us your feedback. We look forward to working with you and talking with you more in the future. Thank you.
Today's busy consulting engineer needs more than just a helpful website. You need a trusted advisor and guide for insight and support. With our new Consulting Engineer web portal, Schneider Electric is just that, an expert source for product information, a seasoned second opinion, a layout specialist, a news and information resource, your own customized support system that makes you, your projects, and your business better. Product catalogs, technical support, codes and standards detail, specs, layout and coordination tools, expert insights, and industry updates are all as close. Today's busy consulting engineer needs more than just a helpful website. You need a trusted advisor and guide for insight and support. With our new Consulting Engineer web portal, Schneider Electric is just that, an expert source for product information, a seasoned second opinion, a layout specialist, a new... Today's busy consulting engineer needs more than just a helpful website. You need a trusted advisor and guide for insight and support. With our new Consulting Engineer web portal, Schneider Electric is just that, an expert source for product information, a seasoned second opinion, a layout specialist, a news and information resource, your own customized support system that makes you, your projects, and your business better. Product catalogs, technical support, codes and standards detail, specs, layout and coordination tools, expert insights, and industry updates are all as close as a simple click. Got a product question? Access our enhanced digital version of the yellow binders you may have used in the past. Digest Plus gives you instant online access to Schneider Electric's entire product line with technical, application, and layout information on our complete product catalog. Trying to choose the right circuit breaker? The Selective Coordination tool lets you quickly test various system and breaker combinations, allowing you to conduct preliminary analysis on the fly. With your product selected, you can configure and insert them into your design in seconds with our Layout Fast app. The Schneider Electric Consulting Engineer portal allows you to make quicker, better informed decisions that you can apply immediately to your project plan. Speaking of staying better informed, your portal is also an ever-changing information hub with continuous updates on products, industry news, and educational opportunities. A quick scroll through the homepage gives you instant access to our ARC Flash Resource Center with industry white papers, webinars, and analysis on today's most complex code issues. Technical specs, codes and standards, and a BIM library with small, rich product model files you can download. A powerful product FAQ tool for quick answers to your most common questions. A comprehensive white paper library with the latest engineering insights and best design practices. Up-to-the-minute industry news with continuous updates on events, tools, products, practices, anything relevant to your business. And to stay